Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we were discussing about the memory management and the paging schemes. We have seen that the paging scheme provides the mechanism by which there is minimum fragmentation, and the fragmentation happens because of the last page only. So, paging scheme is one of the best schemes of the memory management, where we are making use of the main memory to the fullest. Now, with the paging scheme, we have also seen that to speed up the logical address to physical address conversion, we can make use of the translation leukocyte buffer. The translation leukocyte buffer is a kind of the associative memory which is providing us a parallel search. Now, if in case the search address is found there in the TLAB, then we will only have to make one reference for finding out the location or referring to the instruction. Otherwise, we will have to search the page table. That page table also resides in the main memory. It means there will be two page references for searching out any pages, searching out any instruction in the page. Now, later we discussed about the concept of the hierarchical paging and inverted page tables and the hash page table, and we have seen that when the page tables are getting larger, we will have to make use of any of these schemes, so that we can reduce the number of memory slots or number of frames occupied by these page tables. Further, we have discussed about the schemes in which the demand paging has to be established, wherein we are not bringing all the pages of a process at the same time, but we are bringing only the small number of the pages which are active at the moment. So, we have discussed the concept of the virtual memory, and then we have discussed the concept of the demand paging. So, we will elaborate more about the demand paging and the virtual memory system, and then we will see the page replacement algorithms in today's lecture. So, the outline of today's lecture will be that we will first have just a quick recap of the paging scheme, and then we will see the virtual memory and the demand paging that we discussed on the last turn. Then we will see the page replacement algorithm, and finally, we will discuss about the thrashing. Now, just a quick recap of the paging scheme. What happens in the paging scheme, that we divide our process into the equal size chunks known as the pages. For example, if we have a 100 byte size page process, then we can divide it into the 20 byte pages. So, there will be 5 different pages, and these 5 different pages will be accommodated in the equal size main memory chunks known as the frames. Let us say this is the main memory chunks. So, these are also of the 20 byte each. Each of the page will be accommodated in one of the frame. To accommodate the new process, we need to maintain the free frame list, and free frame list contains the list of all the frames which are free at the moment. We need a linked list kind of the data structure that maintains all the free frames, and as soon as the new process comes, we will be allocating them the frames according to the free frame list. If a process exits, then the frames becomes free. So, those frames are also added in the free frame list pool. For conversion of the logical address to the physical address, we need a page table in between. The page table stores the information about all the pages and its location in the main memory. It means the frame number in the main memory. Page table also contains more information, but that is not the matter of the concern here. We will discuss it later. So, we have discussed about the virtual memory and the demand paging. The virtual memory simply means that my process from my point of view or from user's point of view is very big, and it is divided into the pages. Now, what we think that my entire process is stored in the main memory, but this cannot happen because my process can be very big. Let us say my RAM is of size 4 GB and my process is of size 2 GB. In case we bring all the frames of my process in the main memory, so 4 GB part or 4 GB is not only for your process, this is also for the operating system. So, let us say the operating system occupies 2 GB of the space of the RAM, then 2 GB of your process, it means you can run only one process at the moment. So, your system has become uni-programming, then you wanted it to be the multi-programming system. So, to maintain maximum number of processes in the main memory, we need the concept of the demand paging. Now, what is actually we are referring to, that the process has only a small part of that process will be active at any moment. So, why not bring only the active portion of the process in the main memory while leaving the other part somewhere else, and when demanded the new part will be brought from some place to the main memory, and the old part which has actually completed its execution will be sent back to that part. So, we are actually referring to some system in which the hard disk space or some part of the hard disk is treated as the virtual memory. It behaves like the main memory, but it is actually not. So, when process is created, that is divided into the pages, and in the form of the pages the process remains there in the hard disk only, but when a page is required for the execution, it is sent to the main memory. So, depending on the requirement, the pages are sent to the main memory. Now, when these parts complete, this is sent back to the hard disk, and the new parts are brought from the virtual address space or virtual memory to the main memory. So, we are actually bringing the pages only on demand. We are not allowing the pages to remain in the main memory throughout. So, on demand the process pages can be brought in from the virtual memory. Now, this is what we have actually discussed, that when a process is completing, its pages are swapped out to the virtual space, and the new process is swapped in, or the pages of the new process is swapped in from the virtual space to the main memory. So, it is not only for the new process and the old process, this is also for the same process. For example, when the program A is running, it may only require 4 pages for the execution, okay. But as soon as the execution of these pages complete, the new pages will be required. So, those pages will be brought from the virtual memory to the main memory. Now, to maintain which part of your page, or what are the pages who are there in the main memory and who are not. So, for maintaining this, we maintain a page table, and you know that in the page table we can maintain a bit known as the valid and the invalid bit. So, with an example you can see that this is the process, and in this process there are 8 pages, and those pages are numbered as 0 to 7. So, out of this only 3 pages are there in the main memory. Those pages are 0, 2 and 5. So, page number 0, page number 2 and page number 5. Page number 0 is stored in frame number 4, page number 2 is stored in frame number 6, and page number 5 is stored in frame number 9. It means that page number 1, page number 3, 4, 6 and 7 are not stored in the main memory. So, for all those processes which are available in the main memory, the valid bit is set 1 and rest of the bits are set as invalid. Means for other processes, other pages, the bits are set as invalid. So, in case we refer to any instruction and that instruction relates to a page, in case we go to the page table to refer to that page number and we find that there is an invalid bit, meaning that that page is not present in the main memory. So, we will have to bring that page from main memory to that place, means in the bring from the virtual memory to the main memory. So, fetching the required page from the virtual memory to the main memory is called the swap in operation, and when we are sending any old page from the main memory to the hard disk, this is known as the swap out operation. So, several swap in and the swap out operation will be required when the process executes. When the process gets executed, several swap in and swap out operations may be required. Fine. Now, if a page referred is not found in the main memory, we call it a page fault. Okay, we call it a page fault. Several actions are performed whenever the page fault occurs. We will discuss about the page fault in detail later, but it is just that several actions are being performed when the page fault takes place. When page fault takes place, we may bring new page from the virtual memory to the main memory. It may also be required that whenever we are bringing the new page, any old page will be sent back. So, it means that we are replacing the new one with the old one, or sorry, we are actually replacing the old page with the new one. So, we are actually doing the page replacement. Since we are doing the page replacement, there can be several mechanisms to find out which method to use for the page replacement. So, the main task of today's lecture will be that we will discuss about that what method we are going to use for the page replacement. Okay. So, now what will happen in the page replacement, since we have limited number of frames in the main memory per process, in case let us say we are increasing the number of processes. So, this will increase the degree of multiprogramming also. So, degree of multiprogramming is increasing, it means degree of multiprogramming is increasing, it means we are actually improving the throughput of the CPU also, that more number of jobs will be getting completed in the moment. Now, page fault that we have already discussed. Now, we have to discuss about the page replacement algorithm. So, there are many page replacement algorithms, but out of which the most famous ones are the optimal, LRU and FIFO page replacement. So, what does FIFO say? FIFO say that the order in which the pages have arrived. In case you have to replace, then you replace it with the older page, the one which came first in the main memory. Then the LRU scheme says that you maintain a record that which frame is referenced now and which frame is referenced earlier. Okay. So, the latest referenced pages should be there in the main memory, and the old reference pages should be going out for bringing the new pages in. पुराने पेज को या ऐसा पेज जो कि कम बार रेफर हुआ है, हम उसको रिप्लेस कर देंगे न्यू पेज से, लेकिन जो पेज ज़्यादा बार रेफर हुआ है या जिसको रिसेंटली हमने रेफर किया है, हम उसको रिटेन करेंगे. Similarly, optimal means optimal requires that we have the record of the future references as well. Along with the current reference, we need to have the future reference as well. So, अगर future में मेरा पेज रेफर होने वाला है, तो हम पेज को रोक लेंगे, और अगर वो काफ़ी बाद में रेफर होगा, काफ़ी लेट रेफर होगा, तो उस पेज को हम निकाल के न्यू वाला पेज लेके आएंगे. फाइन. सो दिस इज दी three basic or those page replacement algorithms which are used in most practice, but other are also there. The MRU, the most recently used, least frequently used, and many other, or you can do some kind of the replacement like the random replacement also. Okay. So, there are many other page replacement algorithms. So, we will see these three techniques, optimal, LRU and FIFO in detail. So, whenever a process is referring to any instruction, then that instruction belongs to some page. So, obviously, the CPU will be referring to several instructions, it means the several page numbers in the while executing a process. So, all those references is known as the reference string. So, let us say for example, the CPU is referring to page number 7, 0, 1, 2, 0, 3, 0, 4, 3, 2, 3, 0, 3, 2, 1, 2, 0, 1, 7, 1. So, these are the references. Okay. So, we have to find out how many total page faults are occurring. So, what I have said about the page fault, that if the reference page is not found in the main memory, this is a page fault. Okay. For page number 7, it is not there in the main memory. So, we will bring it from the hard disk. So, there is a page fault. Putting a tick mark below, it means that there is a page fault. Now, 0 is also not present in the main memory. So, let us bring this 0. We have already the free slot for this process in the main memory. So, what is being said here, that we are only allocating 3 frames to the given process, not more than 3 frames. If the 3 frames are busy and the new page is coming, some older page will be replaced. Okay. So, there is a page fault, 0 was not present. Now, a frame is present. Let us bring this 1, but 1 was not present. So, here we will consider that there is a page fault. Now, 2 is not there. So, we will have to bring 2, but at the cost of some replacement. So, which will be replaced or which page will be replaced? 7 was the first one to be referred. So, we will replace this with 7. So, 2, 1, 0. 7 is being thrown out to the main to the hard disk. So, there is a page fault. For 0, 0 is present here. So, let us maintain the same order and we will say that there is no page fault. So, cross means there is no page fault. Now, 3. So, to bring 3, we will have to send 1 page out. So, obviously 0 will go because 0 is the oldest one. So, 3, 2, 1. So, there is a page fault. Now, 0 is referenced. When 0 is referenced, 0 is not present. So, we will have to send some page out. So, 1 will go. So, 0, 3 and 2, there is a page fault. Now, 4 has to come. Again you see To bring 4, 4 is not there in the main memory, so we will have to send one page out. So 2 will go. So 4, 0 and 3. So there is a page fault. Then to bring 2, we will again have to remove 1. So obviously 3 will go, 3 is the oldest one. So there is a page fault. So 3, reference of page number 3, again a page will go, so obviously that will be 0. A 0 is coming, again one page will be replaced. So that will be 4 because 4 is the oldest one. There is a page fault. Reference of 3, 3 is already there in the main memory frames, so there will be no page fault. So we can maintain the same order. With the reference of 2, 2 is also there in the main memory frames, so there is no page fault. When 1 is referenced, there is again a page fault. So the oldest page will go, that is 2, there is a page fault. Then with the reference of 2, one page will go, that is 3, so there is a page fault. A reference of 0, 0 is already there in the main memory, so we will have no page fault in this case. A reference of 1, again 1 is present in the main memory, so there will be no page fault. 7, there is a reference of 7 and 7 is not present, so oldest page will go and new page will come. So 0 is the oldest page, so there is a page fault. So reference of 1, 1 is already present, so there will be no page fault. So here you can see that there are total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13 page faults. And how many references were there? 1, 2, 3, 4, 5, 6. The total references were 19. So the page fault rate will be 13 by 19. So page fault rate here is 13 by 19. Now let us see the LRU scheme. LRU scheme says that whenever the new page has to come, the latest reference page will be retained and the page which is least referenced और सबसे पहले रेफरेंस हुआ था उसको हम निकाल देंगे. ठीक है, लेट्स सी विद दिस एग्जांपल. 7 comes, 7 is not present, so there is a page fault. 0 comes, there is no page 0, so page fault. 1 comes, page fault. 2 comes, 2 is not there, so obviously we will have to send one of the page. So here no page has been referenced twice or thrice, so obviously we will allow the first in first out scheme only. So 7 will go. So by the time there is a conflict, we will use the first in first out. Then 0 comes. 0 is the latest reference of this. 0 is present also and 0 is referenced. So bring 0 on the top side. This is just a diagrammatic representation. You will have to maintain some order or some bits to ensure that the referenced bit is set for a page. So we have brought 0, it means 0 is latest referenced page. Now 3 is coming. When 3 is coming, there will be no page fault. Sorry, there will be a page fault. So we will be sending the least referenced page, that is 1. Then 0, 0 is again referenced. So we will again bring 0 on the top, meaning that 0 is currently referenced, no page fault in this case. Then 4, 4 is referenced, we will replace it with the least reference page, that is 2. And then 2 is coming, 2 is not there, so again a page will go, that page will be 3. Then 3 is referenced, again a page will go, so that will be 0 number. So page on the downside is considered to be the least referenced. Okay, the one which is latestly referenced is put on top. Then 0 is coming, so 0 is also not present, so let us send 4 to bring 0. Then 3, bring 3 on the top, no page fault. Then 2 is referenced, 2 is also present, so bring 2 on top, no page fault. Then 1 is coming and there is no page like 1 here, so we will have to replace it with the least reference page, that is the 0. And then we have 2, so bring 2, we are bringing it on the top, there is no page fault. 0 is referenced and 0 is not here. 3 will go and 0 will come. Then 1 is referenced, 1 will come on top, no page fault. And then 7 is coming, when 7 is coming, some old page will go, that will be 2. 1 is referenced, 1 is present, brings 1 on top, there is no page fault. So the number of times page fault did not occur is 1, 2, 3, 4, 5, 6 and 7. It means 12 times the page fault occurred out of 19 references. So page fault rate in this case is 12 by 19. Okay. Now the optimal page replacement. Optimal page replacement, while replacing the page, will see the future references as well. In case the future reference, in case we find that a page is going to be referenced next, we will retain that, and in case the page is going to be referenced very late, we will consider that that page can be replaced. Now 7 is coming, no page fault, 0 is coming, there is, sorry, 7 is coming, a page fault, 0 is coming, there is a page fault, 1 is coming, there is a page fault. So page fault occur in these two cases. Now 2 is referenced and we have to replace a page. So we will have to see when will 1 be referenced, when will 0 be referenced, and when will 7 be referenced. So if you see that the reference of 1 will come here, a reference of 0 is coming here, and reference of 7 will be here. So obviously 0 will be referenced first, so we should retain 0, then we should retain 1 also, and 7 will be very late referenced. So let us replace 7. So to bring the new page, we will be replacing it with the 7. Okay. Now let us maintain a record. We are just removing this. We are maintaining a record of which page came first and which did not came first. This is because we want to maintain the first in first order also, first come first serve order also. So 2 will come on top and these 2 will be like this. Okay. So there is a page fault and we replace 7. Similarly, reference of 0, no page fault. Reference of 3, we will send one of the page out. Okay, we will be sending one of the page out. So 0 will be referenced here, 2 will be referenced here, and 1 will be referenced here. It means 1 will be the late reference. There will be late reference of 1. So we should replace the new coming page with 1. Okay, so 1 has to be removed. So if 1 has to be removed and we are bringing this 3, so the arrangement will be like this. There is a page fault. Now 0 is referenced. Let us retain 0. After this we have 4. So for bringing 4, we will have to send either 3, either 2 or 0. So you can see that 0 will be referenced here, 2 will be referenced here, and 3 will be referenced here. So 2, 3 and 0. 0 will be the late reference, but 2 will be required just next. Okay. So we will retain 2 and 3 and we will send 0 out. So for bringing 3, we are sending 0 out. Okay. So there is a page fault. Now for bringing 2, for 2 reference, 2 is already there in the main memory, so no page fault. 3, no page fault, already there. 0, yes, there is a page fault. So since there is a page fault, we will replace this 0 with some, we will select a page from the main memory frame to bring 0. So 4 will not be referenced at all. 3 will be referenced here and 2 will be referenced here. So we will replace it with 4. So let us bring this 0 in the place of this 4. No, there is a page fault. Now for 3, 3 is already there, no page fault. 2 is there, no page fault. 1 is there, we will have to send one of the page out. So just see, 0 will be referenced here, 3 will not be referenced, and 2 will be referenced here. So obviously we will replace it with 3. So 1, 0 and 2, there is a page fault. For the reference of 2, 2 is already there, so no page fault. 0 is already there, so no page fault. 1 is already there, so no page fault. When 7 is coming, 7 is not there in the main memory frames. So which one should we select? Should we select 1, 0 or 2? So 2 will not be referenced, obviously, you can see in the later references. 1 will be referenced, yes. 0 will also not be referenced. So either we will have to replace 2 or 0. So, there is a conflict between 0 and 2. So, which one should I select? The one which came first. Okay. So, out of the 0 and 2, 2 has come first. So, we will replace it with the 2. So, to bring 7, we are replacing it with 2. So, I already have told you that whenever there is a conflict, you have to involve first in first out technique to resolve that conflict. Okay. Now, 1 is coming, 1 is already there. So, there will be no page fault. So, the number of page faults are 1, 2, 3, 4, 5, 6, 7, 8 and 9 out of 19 references. So, the page fault rate in this case is 9 by 19. Okay. So, 9 by 19 is the page fault rate. Similarly, you can solve several questions with the different examples. For example, this is for the this again is for the optimal page replacement with the same number of the reference string, but with the number of frames as 4. You can do it with the LRU also. Okay, you can select the LRU scheme also to do this. Let us say we are doing it with the LRU. Let us do it fast. 7 is reference not present, 0 is reference not present, 1 is reference not present, 2 is not present. So, there is a page fault for all these cases. 0 is reference and 0 is present, bring 0 on top, no page fault. 3, replace it with the oldest one, there is a page fault. 0, bring it on top. 4, replace it with 1. 2, bring it on top, no page fault. 3, bring it on top, no page fault. 0, bring it on top. 3, bring it on top, no page fault. Similarly, 2, bring it on top, no page fault. 1, you will have to replace it with someone. So, 1, 2, 3, 0, replace it with 4, page fault. 2 is already there, bring it on top, no page fault. 0 is already there, bring it on top, no page fault. 1 is already there, bring it on top, no page fault. 7, we will have to replace it with the old page. So, 7, 1, 0, 2, page fault. 1 is already there, 1, 7, 0, 2, no page fault. So, the number of page fault here are 1, 2, 3, 4, 5, 6, 7 and 8. It means the page fault rate in this case is 8 by 19. It means by increasing the number of frames, here we can see that the number of page faults have reduced. So, we will see in the next lecture that how increasing the number of frames is affecting the page faults. Fine. Now, we can solve all the questions by yourself. And let us say there is a question, a memory page containing a frequently used variable that was initialized very early and is in constant use is removed when, meaning that a page is frequently used, even then it was removed. Okay. So, a page is frequently used, even then it is removed. If a page is frequently used, by the LRU scheme, that will be brought on top. Okay. And a page is used and least, we are actually maintaining the number by how many times a page has been referenced. So, we will only replace the least frequently used. So, LFU scheme also can also not be there. So, only possibility is that the FIFO algorithm will replace that page. Okay. So, because LRU and LFU are taking care of these things, that anything which is referenced latest, that has to be retained, but FIFO is not doing that. So, FIFO scheme will be the answer of this question. Now, let us take this question. Increasing the number of page frames sometimes increases the number of page fault. Okay. Second is saying some programs do not exhibit the locality of reference. Okay. Both are fine, both the statements are true, because we have still not proven that by increasing the number of frames, the number of page fault reduces. In fact, there are some of the schemes in which it does not reduce, in fact, it increases. So, the P statement says that increasing the number of page frames sometimes increases the number of page fault. Yes, it is true. We will see in the next lecture that in the FIFO algorithm, when we increase the number of frames, the page fault increases. The Q says that some of the programs do not exhibit the locality of reference. It means we are actually referring to the concept of the caching. So there may be some of the programs which do not exhibit the locality of the reference. There are frequent calls from one function to the other, then that function to the other. So obviously they will be lying in the different portion of the memory. So they are not exhibiting the locality of the reference concept. So P and Q both are correct. Yes, it is correct, but Q is not the correct explanation. There is no relation of the Q and the P. Okay, there is no relation of Q and P. So hence you should consider that P is correct, Q is correct, but Q is not the correct explanation of P. Now let us study the last concept for today. Let us say we are in the system and we are increasing the degree of multiprogramming. Obviously, if we are increasing the degree of multiprogramming, the CPU utilization will be getting better. Okay, CPU utilization will be getting better. But when we are increasing the degree of multiprogramming, actually we are reducing the number of frames. When we are reducing the number of frames, then the page fault will start increasing. Okay, you had 4 frames, then 3, then 2. Obviously, the page fault rate will increase. When the page fault rate is increasing, it means that we will have to bring new pages from the main memory to the from the hard disk to the main memory. So it means that frequent page fault के केस में हमें ये एक्टिविटी करनी पड़ेगी. इसका मतलब CPU उसी प्रोसेस में बिजी हो जाएगा. So it means the CPU utilization will again go down. So this actually is the concept of the thrashing. So in the next turn we will discuss about the Bellardi's anomaly, and we will discuss this concept of the page fault in more detail. Thank you.